Thanks so much, John. And if the panelists can join us here at the table, we will dive right into a discussion. Very, very rich session, a lot to consider. I wanted to kick us off with a question that has been in my mind throughout the session, and I set this up this afternoon session as being focused on populations. And I heard a fair amount of attention to that, and even more attention, obviously, to exposures. So my question for the panelists has to do with, and very much with Dr. Mukherjee's points this morning, when we think about conventional approaches to biostatistical probability and selection, who are in the populations that you're studying and who's missing? So that's an element of uncertainty, and I think also related to vulnerability and susceptibility as well. So as you assess the data sets that you're using, what are you dissatisfied with? Who's missing?
I'll start off. So we all looked at the Haynes data set, at least in passing. Haynes is fantastic in some respects. They oversample pregnant women, for instance. So we actually have additional data there. On the other hand, they're not taking blood from children under the age of 6, and I don't blame them. I have a 6-year-old. I would never try to get blood from him. They also don't have occupational exposures. So everything I was just talking about is for the average person. If I work in a factory where we work with that chemical, I know nothing about that. So Haynes does a great job for just characterizing the average American, but none of us are the average American, really, at the end of the day.
And Raj, I know you've been working on Haynes as well, and I'm eager to hear what Scott thinks about his extrapolation of images. So.
Yeah, so I completely agree with that. I'll add 2 points. So with Haynes, I think racial demographic diversity is in some sense captured by Haynes in ways that it's not in many local data sets that are available to us. And so we've been doing a lot of work actually in looking at, both in the context of environmental exposures and just in looking at common blood labs and how we set reference ranges for common blood markers across demographically diverse populations. And Haynes is a very powerful data set to do that in sort of one respect. But then there are things like, before 2011, I think Asians weren't a separate sort of category, and everyone's just sort of lumped into other. And so it gets tricky to really get kind of fine resolution, which you need to do for many things. And then the other broad point related to that, but I think also more generally, is that it's hard to link some of these data sets with other data sets that we'd like to. So I think in Haynes, you can have access to some genetic data in a limited way, which we haven't used ourselves. But even things like, there's just a JEMA paper today, but using race or ethnicity and conflating that with ancestry or genetic ancestry is something that I think is important for basically everything that we do when we think about how we adjust these models and how we ascribe causality or we ascribe sort of significance to certain exposures. So it's not possible to do that, and a lot of the time when we say ancestry, we mean race, and when we say race, we mean ancestry. So I think the degree to which we can make genetic data in addition to what's provided already safely available to the community at large, which we actually do have fantastic examples from other cohorts like UK Biobank and some of these other ones. I think that would be fantastic. So I would love to see NN Haynes with some genetic data. I'd love to discuss that as well too.
And then, Scott, I was thinking that was my burning question during your presentation is how do you take your models and how do you immediately upload population data? So how quickly extendable are your exposures to individuals? And I know you're doing direct modeling as well. So can you help us think about that?
Yeah, so it depends, I guess. So for chronic studies where you're really just looking at sort of between city differences, so long-term exposures, the satellite data for PM2.5 probably does a reasonable job of capturing between city differences. And so those models are very easy to implement if you have a cohort to apply to. The challenge is that we don't have monitors everywhere. So basically there are no monitors in Africa. So the model's only going to do a good job at predicting where it's seen something similar. So if there are places that are drastically different than something that's in the training set, our exposures aren't going to be very good. The one thing that we've been talking with the GBD people about is that because the GBD DIMAC model is a Bayesian model, we might be able to use our image model as sort of to give some prior information as a kind of a best guess before you add on the additional information. So it might be the combination of the two would be better. Now, what was sort of the other aspect of the?
Well, actually, you mentioned cohorts. How readily available are those data? Are cohort data that you could quickly incorporate to, achieve that intersection?
Depends where you live or where you want to work. So in Canada, we're lucky we have a lot of openly available cohort data. So our entire national census has been linked to health records, so mortality, cancer incidence, and also tax records, so that we can follow people over time. And so a lot of the air pollution work that we do, so if we have an exposure surface for a city, we have a population representative sample in that city that we can link up to. Now, we already have good models for Canada. I think Canada's not really the mecca of air pollution concerns in the world, right? I think where these models are going to be useful is in trying to provide some information to places that might not otherwise have it. Right, so if we can leverage information on exposure and images in places around the world, maybe we can then generate reasonable estimates in places that may never have, or it might be a long time before they have actual measurement data on the ground. Mm-hmm. So I think that's probably, at least in the near term, the best use of that. The local level images, if it works well, it could end up being a really cost-effective. You can imagine a smartphone application that has audio and images, and if the model is trained well, you could have a little personal app that would sort of use the camera and microphone on your phone that would give you some kind of estimate of your exposure to noise and certain air pollutants. So that's sort of where we're going with that. But again, it really depends, because we're really sampling space, not people, right? Mm-hmm. And so when we do these campaigns, we make sure that we go to every kind of neighborhood, regardless of its industrial area or low SES or high SES. We kind of go everywhere. But we go everywhere in Montreal, right? And so there are limits, and this is why I think we have to leverage everyone doing these kinds of things around the world so that we can all benefit from the work that everyone's doing instead of just reinventing the wheel every single time. Yeah.
And all these models, and this was mentioned right at the start this morning, all these models are falsifiable. And so to some extent, identifying where your model is most uncertain and then saying to somebody, hey, if you're in Africa right now, your 5 measurements of air sample could invalidate or validate my 1,000 measurements in Canada. That's that incentivizes people or take it. So basically all these models are designed to identify their weaknesses, and then somebody can go and take new measurements. And I think that is a place that we really need to say, hey, we don't need another measurement of this, but.
I think maybe one thing that would be efficient would be to leverage some of the sort of community citizen science kind of projects. Yeah. And sort of have a way to link up things like images or audio to those sort of maybe not gold standard measurements, but as a sort of way of sort of getting as much information as possible, at least as a starting point.
Yeah, actually, it makes me think of a workshop that we did a few sessions back, which was on personal exposure monitoring. And we had some innovative approaches to capturing large sets of data. We didn't have the digital imaging, I remember that, so that's new, or the acoustics. So those are 2 elements of exposure that we hadn't thought about previously here at the
I should also say that it's entirely possible that the sound won't work, but I think it will.
We'll stay tuned.
But it's entirely possible that it absolutely will not work. So
we'll stay tuned.
Okay.
So I'm going to ask one other question and then want to turn to folks in the audience for questions for our panelists. And this is a theme, overarching theme from our sessions, and that is about there's sometimes machine learning algorithms are described as a black box, and I heard very clearly from Raj a desire to break that down and to make sure that it's as clear, parsimonious, and transparent as possible. How about for the other panelists, when you think about how your algorithms are working, do you know how they're working? How reproducible are they? Can you lay it out easily so that others could actually replicate?
So, and several people have mentioned that you can identify which parameters are driving these models. And, in my experience, there's a huge bias toward, well, those clearly, whatever parameters the model coughs out, someone will always say, oh, yeah, I knew it was those parameters the whole time. I just neglected to use them. So I mentioned that it's reassuring to me that I can get those, but I've very rarely actually invalidated a model or said, oh, I don't believe the model because, I didn't see this parameter or I do see that parameter. It's really hard once I see the list of parameters to mentally separate that. So that is a concern to me, but at the same time, my cognitive bias makes me happy, so I don't know.
So I guess two things. For the convolutional neural networks, of course, they're still sort of a black box, but I do like the idea that you can highlight and sort of have a visual representation of what's actually being used. And so the fact that the model is learning sort of combinations of colors and shapes that make sense gives me some sort of degree of satisfaction that it's actually learning something that makes sense. Also, I didn't present this, but we did a global map of of the difference between our model and the GBD model. And the places where it disagrees most are places where the GBD model estimated PM 2.5 from PM 10. So, and our model is only based on PM 2.5 measurements. Mm-hmm. And so that also sort of gave me another level of sort of satisfaction that, okay, maybe it's not just really good luck.
You could
really
pinpoint the source of error, actually.
Or just the fact that because we had a slightly different approach in these specific places, that was where it was like whole countries were like basically lit up because there are certain countries that have a lot of PM 10 data, but not PM 2.5 data. Mm-hmm. And so that again was like another check on if we're actually estimating what we think we're estimating. But at the end of the day, there's millions of parameters in these models. And so it's not like a regression model where you can sort of get a coefficient and say, so it's the distinction between prediction and inference, I think, is always the important thing to keep in mind, right?
Yeah, so. It's an important theme for today. Let me turn to the members of the audience for questions. Gary.
Go ahead. All right. So something I think a lot about with machine learning models.
If you could speak into the microphone for the folks on the web.
Something I think a lot about with these models is what happens when the model replaces the test or replaces the real property. Is that good or bad? I think there's a book about this called Weapons of Math Destruction, where like a model replaced an educational test, right? And people then optimize against the model. So they're going to make sure they do really well in that model, and they stop caring about the test because it's not done, right? So for the sort of CNN on PM 2.5, a good example of it going well is like you identify, hey, this truck is really bad, and a city who's trying to optimize their score for PM 2.5 says, let's get rid of that truck. And it turns out it's a really bad truck, right? But a bad example would be they spray paint all the roofs of their buildings green because that really helps with the model, right? And just for the sort of like constructing new substances, you can imagine using the use case model and saying, the use case model says I'd never put this in a pigment. So I'm going to put it in the pigment because it doesn't change my score at all for, this outcome. So that would be another misuse, right? So I just wonder if you think about that all, what your thoughts are on that stuff.
Well, somebody said earlier, the idea of machine learning is that new data makes machine learning models better. And I guess the corollary to that is something Nate Silver says is that, there is no ultimate model. There's the best model you've built with the data you have today and the data you're aware of and the techniques you have today. And if we can massage that in getting models like this adopted for regulation of this approach produces a good model, but the particular value of 0.336 on parameter 12 is reflective of what I know today and not what I know tomorrow. Or, it's a hard thing to say, but basically don't treat a model as a fixed thing to be optimized against. Treat every set of data as an opportunity to learn something more, which is hard because you make legal decisions based on it. You don't want somebody to have a legal decision made today and then I optimize my model tomorrow and say, oh yeah, different story today. That is a real challenge.
I'll add to that. Yeah, I completely agree. I think your question just it points to the need to update our models and update the training process with new data. I think we have many big examples of this already. Google Flu trends, secular trends, changes in searches over the years. I think also it points to the need for continuous real-time validation that I think is easy to talk about but very difficult to do. But in many ways that can be separated out as different than sort of the model training and the model creation process itself. But how do we validate these things once they're deployed in the wild? I think it's a very open and very, very important question.
We have time for just one more question.
So Gary Miller, Columbia. When I was a graduate student over 20 years ago, I remember being asked by my advisor about all the ingredients in a kit I was using to isolate something, the sort of black box we're talking about now. And it was easy to say, well, what's reagent A, what's reagent B? But as now an advisor of students that are using some of these approaches, is there guidance on how you ask those questions? Like, what are the key questions to open up the black box, the algorithm structure, the sort of data in there? Like, how do you guide the people that are overseeing people trying to do this who don't quite have that expertise?
Very carefully. So early on, I'm not sure this answers your question, but so early on we were starting doing this and we thought, oh my God, this model is just amazing and it's predicting so well. And we realized we just did a really bad job of splitting the data. So there were the same examples in the training versus and it's easy to do that when you're starting out. And so with these models, our experience has been sort of the more careful you are, the worse your model does. Because it will just optimize whatever you give it, right? So you have to be very, very careful in how you separate your data sets out. And I think just learning that just because you get a result you like, maybe that in that particular case you should be the most skeptical, right? So like always doubt what you're getting and make sure that you don't just stop searching because you like the answer you got. Because we certainly did. There were some sort of growing pains at the start, but I don't know what you guys think.
I mean, the one thing I would say is just training people how to do machine learning like it is going to be done here is probably the most important thing, because probably the person who's going to write the textbook on how to do it correctly hasn't even been shown how to do machine learning yet. And we need to have more people who have experience with how to use these tools and how to screw up with these tools. Yeah, it's a hammer and everything looks like a nail, but sometimes it's your thumb. And people need to have that experience, and we need to go into it with the idea that this is a new powerful tool, and we're going to have some learning experiences, as one of my friends used to say, euphemistically.
Okay, so we are going to end now for a half an hour break. Can we give a round of applause to our panelists? Thanks very much.